Hello class and welcome to the next lesson. Today I'm going to be talking about refraction and transmission of waves. And they go hand in hand. Section 6 of the textbook talked about the transmission of waves. We know that waves experience reflection and transmission upon reaching a boundary. And the ratio of one to the other just depends on how much energy the wave loses upon reaching the boundary. As in, some of the energy can be fully transmitted and a very small reflection, or most of it can be reflected and very little transmitted. But I want to bring up refraction when talking about the transmission of waves. So we're kind of circling back just a little bit. And to start talking about this, imagine I had a ripple tank. When I say a ripple tank, I mean it would be a lot easier to show this in real life because your teacher actually has a ripple machine that we can look at water waves on and kind of make observations from it. But for now, let's just pretend we had a ripple tank and we were noticing waves propagate across the surface of the water as such. Now, they would have some sort of wavelength and they'd be traveling at some sort of velocity, which means that their frequency would be velocity divided by their wavelength. Now, that frequency can be set to a certain number. Now imagine we had the ripple tank and maybe in the middle we placed a slab in there of some height. What this ends up creating is a sort of partition of two mediums. Medium 1, where the water is deeper, and medium 2, where the water, which is up here, is shallower. Now the thing about shallow water is ripples will travel at a lower velocity through the shallower water. Why is this important? Well, the source frequency isn't going to change. This source frequency is going to maintain its value. So if this frequency here in medium 2 is equal to the frequency of medium 1, but the velocity in medium 2 is less than the velocity in medium 1, well, it goes to show then that the wavelength of the ripples in the first medium is going to be greater than the wavelength of the wavelength in the second medium. So you would see things, it would kind of look like this, okay? So this is wavelength 1, traveling at velocity 1. This is velocity 2. This is wavelength 2. And velocity 2 is less than velocity 1 because this is shallower. Now, why is that important? Well, again, we have to think of waves in more than just one dimension. We could have, let's consider this an aerial view of our ripple tank. And on this side, I'm going to have the first medium. And on this side, I'm going to have the second medium. We're going to have an aerial view, and instead of the waves coming in evenly with the normal, we're going to set them at some sort of angle, okay? Here's our normal. And while I'm going to draw it to you, I'm also going to post a simulation here in a little bit that you can watch next of 2- and 3-dimensional views of this phenomenon. See, let's say, again, here's the deeper water and our ripples are emanating in this direction. Maybe our ripples, and they propagate in a circular fashion, but they're propagating in this direction with respect to the normal. And then here in medium 2, we have our shallow water. Remember, I placed a slab in the ripple tank. Well, we're gonna notice refraction. Now, refraction happens in such a way that we notice a change in the wave direction at the boundary between these two media. So here, and then here's my angle with respect to the normal. We notice that my incident angle is not equal to my refracted angle. Here R is going to be refracted. Of course, we're also going to have a reflected angle, a reflected wave with the same wavelength as medium 1, maybe it's lower amplitude because there's some energy exchange between the boundary, but it's going to have the same angle as this incident, as opposed to the refracted wave, where the refracted wave is at a different angle than the angle of incidence. Now, this is basically a precursor to something known as Snell's law, which is possibly something you've heard of before. When we start talking about especially optics and how light behaves as a wave, we are really going to get into Snell's law. And what it boils down to is the fact that velocity through various media is different depending on the properties of the medium, and the angle that we can expect the waves to refract at obeys a mathematical function described by Snell's law. So like I said, we will talk about that, but I wanted to mention that the law of refraction will depend on the properties of the two media. And here's the other thing too, the wavelength of these wave fronts is going to be different. Since the wave travels faster through medium 1 than through media 2, this wavelength here, wavelength 1, is going to be larger than this wavelength here, wavelength 2. I didn't do the best job of drawing that out, but like I said, I'm going to be posting a simulation where I can make this more apparent. Anyway, that is the refraction of waves, and that's all I have for now. Until next time.